Welcome to the satellite communication course. Today we will learn that a code division multiple access system CDMA. Now we have learned earlier that FDMA system in a FDMA system that frequency spectrum that will be divided, and in a TDMA system that time slots are divided. So we can make a communication through this technique. And another multiple access technique is called as a CDMA. So in this CDMA technique, a user can use the entire spectrum. User can use the entire spectrum for all the time. Now, in the case of a frequency division multiplexing, that full spectrum is available. So each user can use a part of a spectrum all the time. They are using a part of a spectrum all the time. And in a TDMA system, users share the available time and they are using a part of the frame. They are using a part of frame and the entire spectrum. Now here in an entire spectrum, part of a frame is utilized, but here in a CDMA, entire spectrum for all the time that is available. So in this CDMA technique, that users share the available power. Users share the available power, and that can be achieved by the combining a data by combining a data with a PN code or pseudonymized code at higher rate than the data rate that was used by the other technique. Now, if you see that here, it combines the data with a given particular pseudonymized code or a PN code. So, see the modulation technique used in the CDMA here, we can say that a PN modulation that will be spread the signal spectrum. So that's why if you see that means that modulation means what, combining a data with a PN code. So that is nothing but modulation that will be spread over the entire spectrum. So that's why this method is called as a spread spectrum, or we can say that it's called as spread spectrum multiple access. So in this technique, every transmitter they have a some PN code, and that PN code which serve as the address of the transmitter means we can say that transmitter has some particular PN code, and at the receiver identify a carrier by detecting that particular PN code corresponding to that particular carrier. We say transmitter transmit the a PN code that is about data and all, and then receiver will detect that PN code. So that is, we can say that by detecting that particular PN code, we will get that particular carrier. So now in this case here, we say that a combining the data with a PN code. So means we can say that a PN code are are superimposed on this data directly or used to change the carrier frequency at each symbol of the code. So there are the two types of a CDMA here. One is about a direct sequence code division multiple access system, DSCDMA, that is a direct sequence multiple access system. And another is what? A frequency hopping code division multiple access. This one is about a direct sequence, and this one is about a frequency hopping CDMA. Now, we'll not go in detail about this, how thus PN codes are generated, but in a CDMA application, each transmitter in the network they have a different PN sequence. So means we can say that a transmitter has a different PN sequence. So if we have the large number of PN sequences there, so then there will be a good cross correlation in this particular technique. So now we can say here for a given length of a PN sequence, so we'll generate that a PN code. So how to generate that PN code? And that is using a modularity adder, or simply we have a polynomials of that particular PN code, and then we can design the PN code using the shift register. So that PN sequence is nothing but a modulo 2 addition, and that is to be used here. So now we start with a direct sequence. Direct sequence CDMA. In the case of a direct sequence CDMA, we say that earlier that it has a PN coded, and that PN code is directly added to the user data, and that will result a PSK carrier. Means we have a PN code that will be added to the data, that is our user data. So we'll get that a PSK carrier. So if you see here a user data, and then we have a PN generator, then we will get that a PSK modulator, then is the IF, then RF transmitter, and then we'll get that DS CDMA signal. So whichever the user data we have, that will be directly added. This one is about a modulo 2 addition takes place to the user data, and then after that we'll get the output that will be modulated to get the PSK carrier. Okay, means we will get that, but whichever the signal here we are getting, that will be modulated by using the PSK carrier. Now this a PN generator, that clock rate of that PN sequence is higher than the data rate. You can say that a is clock rate is higher than the data rate. So that's why whatever the data we are transmitted through this PN sequence, because the spectrum of that data is narrow, and but the spectrum of this particular PN code or PN sequence is wide. If that data has a narrow spectrum and it has a wide spectrum there. No, but if you see that a result means what we have a narrow and a wide sequence, but the resulting signal through this, or you can say that a transmitted data, it has a wide spectrum here. At the receiver, so that a receiver process for this DSCDMA, so it has a input DSCDMA signal, that is the input to the RF receiver. Then this will be the IF signal we have. Here is a correlator. Then a filter detector. Then a detected data. And to this, we have a PSK modulator. And then local PN generator. Now, if you compare the a transmitter here, this one is about a PN generator, that is about a transmitting side, we have the APSK modulator, means modulated output. But at the receiver side, if you see that there is a replica of a PN generator, PN code generator, that is to be used. And that PN code generated, which is a in phase synchronization with a PN code used at the transmitter. So if it is a phase synchronized, then data reception will be very easy. So that's why we can consider here for this a local PN sequence that will be modulated here. That's why we can say that a PN sequence, here we have a PSK modulator, so we'll get that local sequence is modulated here, and the received signal, that will be a correlated, here we have a correlated, and that received signal will be correlated with a locally modulated PN code. This one is about a locally modulated PN code is there, and receiver signal, whatever the receiver signal is generated, the receiver signal we have received, that will be correlated with a locally modulated PN code to get back the whatever the source data, means detected data, whichever the transmitted. So this one is about your a transmitter. This one is about a receiver here. That is receiver what? Direct sequence CDMA. Now we'll continue the discussion with how this PN code is generated, how this data sequence and a PN sequence is generated here. So if you see that we have the a data, then we have a PN sequence generator, then data plus PN, then it will be transmitted. So this one is about a synchronous here. And at the receiver, we have a data plus PN, that is input to this. So natural whatever the this part is about a transmitter, this part is about a receiver. So we'll get that a data here. So now that is about a data recovery. So now how this data is generated. Now you can see that this figure, it is showing that this is about a PN sequence. This one is about a data. Now this is about a process of generating the spread sequence of a modular 2 generator here. Along with that, whatever the data we are transmitting, means we have a PN sequence and a data. This is about a PN sequence, this one is about a data. And then a transmitter is nothing but what? PN plus data. And we have a at a receiver PN, then a PN plus data plus PN here, and then we'll get that that particular data here. Okay, so this one. Now if you see here, the data sequence and a PN sequence, they are a modulator addition here, and it has a 7 bit of a length. One. Okay, so we can consider that whatever the sequence it is generated, that is a PN sequence and a data here, and the data stream is about in the form of a 1 and 0 there, and we'll get that output. Now we can see here that spectrum of that data and a PN sequence and a detected signal. So this one is about a spectrum of a data. This one is because data is a narrow here. This is about a data here, and this one is about a spectrum for a PN sequence. And here we'll get that output. That is a we apply the low pass filter response to this, so we'll get that input here. And this one is nothing but what? Whatever the transmitted signal. So applying that a low pass filter here, we'll get that a output. And that detected signal can be with or without receiver PN synchronization if you apply that a low pass filter here. Now you see here, if we synchronize the PN sequence in a at a receiver side, so what will happen? So suppose we say that here we have a PN sequence and that PN data, and that is about a shifted PN here. We can say that this one is about a PN plus data, or it is supposed to be PN that will be shifted PN. So then we will get that output is about a PN plus data plus PN here. We will not get exactly accurately whatever the data we are transferring if that PN sequence is shifted here. So that's why we need a synchronization of PN sequence so that we'll get that data there. So receiver synchronization is necessary at the receiver side so that we can synchronize the phase of the PN generator. So our aim is about phase of the PN generator. So means for the receiver synchronization, we need to synchronize the phase of the PN generator at the receiver with the phase of the identical PN generator at the transmitter. But it is very difficult to synchronize the phase of the transmitter as well as the phase of the receiver there. So that's why it can be done by the clock of the receiver side PN generator, that is a clock at the receiver side of a PN generator, that to be run slightly higher than the whatever the slot, whatever the clock at the transmitter side. So that's why we can synchronize the PN sequence. So that's why that because of that higher clock rate, the receiver side PN sequence phase then slips continuously and slowly, and that is called as a acquisition phase. When that phase of this both the sequence match, then the low pass filter producing the high output, and then we'll get that a received data. Okay, so we will get that received data likewise. So that is about we will use a filter here, and then we'll get that data. So if you see that in this particular figure here, they are using a local PN generator, and that is modulator with a PSK modulator, and that will be applied to the correlator. So now this is to be whatever the local PN generator used at a receiver. that is to be synchronized with a transmitted PN sequence there. So correlation here takes place from the received data and from this particular PN sequence. The received PN sequence, it is about a PSK modulated here, and that is applied to the correlator. This input is about a PSK modulated we have, and when it is applied to the correlator, so if that phase is synchronized to the received signal, so what will happen? We'll get that is detected data there. So means what we can say that, so that if it is a phase modulated here, then the signal bandwidth is reduced so that the local low pass filter is able to recover the data there. So means at a correlation, so some peak occurs. So that's why your output will be higher here. Likewise, so means then we apply the low pass filter, and then we can receive the data there. So output of this particular correlator, that is a filter model. Okay, applying filter. So whichever the data we are receiving here, because it which it has a sequence, we can say that it has a PN sequence spectrum. But when we apply the filter, so then we will receive only this particular portion. Means that we will get the data here. So it doesn't have a PN code. So it only detect the whatever the data it is to be transmitted. So that's why we should know that how that synchronization is to be takes place in this PN in this receiver there. So whatever the clocks generated at this particular frequency, it is fixed for the given particular transmitter because it is sending the data so that a correlation output we are getting that will be higher there. Now we consider that a PN sequence, what will be the a period of that particular PN sequence. So that generally we say that a PN sequence that will be exactly equal to the data symbol period. So then we can say that here a period of PN sequence that will be exactly equal to the data symbol. Now, if supposed to be what happen, if that particular core, whichever the code we have, and if that code with period shorter than or equal to the data symbol or equal to the data symbol, and that is to be termed as short code. Because short code and a long codes, these terms are used in the direct sequence paired spectrum signal there. And again, we need to know about that a correlation of the PN sequence with a continuous shape, because if there is a time shift of the sequence is continuous, then we can say that the peak occurs at a zero time shift, and within that one bit period of a time on either side from the normal position, the autocorrelation has a triangular shape. So you can say that here it period here Tc, this period again Tc here. That's why we can say that a shape will be what, from this to this, that will be of a triangular shape. And that normalized peak is that R of t is here, tau is equal to 1. When we can say that R of tau is equal to 1 by L for t is not less than equal to 0 there. But R of 0 is equal to 1 means we can say that autocorrelation peaks are separated by the period of a PN sequence, that is of a LTC. This one is about a autocorrelation of the PN sequence. But in the case of a, we say that a course now, short course and a long course. Now we can consider that the code with a period shorter than or equal to the data symbol, that will be termed as a short code. So this is about a short code, and these are about the long code here. So this one is about a data. We have a short PN code sequence of a length 7 chips. That chip is nothing but whatever that rate we mentioned earlier. That is whatever the data rate that we can say. Means we can say that for the clock rate of the PN sequence, also it is called as a chip rate. Okay. Also it is called as a chip rate here. And so that's why we can say that a short PN code length 7 chips, that is about a clock rate we have. So in this case, repeats for each symbol and a L chips of the PN code are contained in each data bit duration of a TDF. So now that is about a LTC here, that is about a shift, and a bit duration, we can say that is about a bit duration for each bit duration here, and this is about a 7TC. So each chip duration is a TC. So we have a LTC is equal to a TD. That is about a, this one LTC is about a duration, and TC here. Okay. So now if we see that waveform from this particular short code and this data, so we are getting that a spectrum of the short code modulated signal, and that signal is periodic with the lines occurring at a 1 by LTC interval. So you'll get that a DSS signal. So similarly, if you consider that a long codes, that long codes are generally, we can say that, whose length, which is generally several data bit long. Okay, now here long PN code. It has, for the long PN code, that length of this particular PN code, which is several data bit long. So that's why long PN code length is about a 31 chips. Here 31 chips. Here is a 7 chips. And if you see that the spreading waveform, that is not periodic with respect to the data symbol. This is about a data symbol. And if you see the spectrum in this case, it looks like a random in nature. So, but if you see that here in this DSS code here, whatever the generated DSS signal, so here that DSS signal is aperiodic in nature, and that DSS signal, that will be a complex for the detection than the periodic short code modulated data. This one is about a short code periodic modulated data. This is about a aperiodic data here. So that's why it is a very difficult. This one is difficult to detect. Okay. Next, we can see that for a given particular data, when we transmit, or we can say that a data is modulated, DSSS data is modulated, the output will be nothing but what we can say that a continuous data. So we can say that a data and a PN data, we can write a data, that is a D of t, and a PN code, we can write that will be P of theta, P of t. And that product of this is nothing but what, a S of t is equal to what, D of t into P of t. So now this signal we are getting after modulation here, when the signal is transmitted through this additive channel, then what will happen at the received signal? So received signal received the signal S of t, whatever the signal transmitted, that is about S of t is transmitted signal, plus some interference signal. Means we can say that a transmitted signal, we have S of t, that will be combined with a interference signal at the receiver. So the receiver signal here, so this is about a transmitted signal, this is about a receiving signal, so it has some interference. So we can see here, so that a signal R of t, that is multiplied with, if supposed to be a PN signal P of t, so means we can say that R of t into P of t, then we will get that the output of the receiver, that can be what, a D of t plus G of t, and that D of t, that will be the data, that will be recovered data after the receiver signal, that will be multiplied with this PN sequence. And that G of t, that is nothing but what, a interference signal is spread with a PN sequence. So that's why data we are receiving as well as the G of t we are receiving, that is interference signal, that will be multiplied with a PN, that is a I of t. This PN means what? P of t into I of t. So we'll get that this G of t there, and it has a spread bandwidth that is as that of a whatever the PN sequence is. So that is about your, we can say that interference effect occurs on this whatever the data. Now next we can consider here that the frequency hopping CDMA, or we can see here in another way, we have the data spectrum, we have a spread data spectrum, then this one is about the interference spectrum, and then we disparate data spectrum. This one we'll get that output here, and we can calculate from this. We can calculate that another part or another component here. Next, we see here a frequency hopping CDMA. Means we can say that FSCDMA. So in this FSCDMA, that carrier is made to hop carrier is made to hop, or we can say that carrier is hopping from one frequency to another. Okay, so that is called as a frequency hopping here, and that hopping is done, or whatever the carrier, we say that carrier is hopping from one frequency to the another frequency, that will be within the allocated within allocated frequency band. Okay, it will be hopping here from one to another, one frequency to another, but within a allocated frequency band, along with the whatever the modulation there. So now we consider here a frequency hopping modulation technique. So in this we can see that a frequency hopping modulated carrier, this one this one is about a frequency hopping a modulated carrier. This one is about a FC. Here we can say that FC. This one FC minus del F. This is about a center frequency FC, and this one is about FC plus del F. So another sequence here. So likewise. So that is about a frequency hopping CDMA here. So if you consider that a FSK system, here frequency hopping CDMA with FSK carrier hopium, we can consider that a binary FSK system that will be modulated with the data at 1 by t hertz. Means we can say that a t symbol. We can say that a t symbol here, and if you see that this one is about a frequency available RF band, and the minimum frequency separation between that FSK tone is a 1 by t hertz, and that available bandwidth RF bandwidth, they are divided into the F1 to FL carrier. It's about F1, F2 up to dash dash, that's about a FL carrier, and that F1 to FL each with a bandwidth of a 2 by t hertz. that is nothing but a modulation bandwidth. 2 by T hertz, that is nothing but the modulation bandwidth. And the carrier frequency is controlled by a PN generator of length L is equal to 2 raised to n minus 1 chips, where n, that is nothing but a length of the shift register that generate the PN sequence. Now typical PN sequence here, frequency of FSCDMA system. So it has a FSK modulator. If I'll draw here, that is data input. Then we have a FSK modulator. Then a channel. Then FSK demodulator. This one is nothing but a transmitter, receiver here. This one is about the data. Will get that output that will be of a data here. So this one, a fast frequency synthesizer. And then PN generator of length that we can say that 2 raised to n. And this one is about a sync information for the PN generator here. So we can say that a sync information for synchronization purpose. We have the same fast frequency synthesizer. So now this is about a transmitting side, FSK modulator, fast frequency synthesizer, PN generator, receiving side, FSK demodulator, fast frequency synthesizer, and a PN generator. That is at the receiver side. So frequency hopping carrier is generated by this fast frequency synthesizer, and PN generator that will provide the control data for this particular synthesizer, and then a carrier is FSK modulated by the data, and then that will be transmitted, and the receiver PN generator is synchronized to the transmit PN generator here, so that it generates the symbol control data for the receiver side. That is about a reception there. So here we can have a synchronization here, and FSK demodulated detects the data that is using a carrier provided by the fast frequency synthesizer. That is about a frequency of CDMA system. So now we can see here in this particular technique what will be the a processing gain and a capacity in a CDMA system, that we will see now. So now that for that purpose, if you see that the processing gain here, that processing gain